Dear friends, a quick presentation of the central problem we face, with statistical inference, with science, with a lot of things in real life. That's called the law of large numbers. How many observations do you need before you can be comfortable that you've seen the thing and you can make a statement? With thin-tailed variables, look, on the left here, we're looking at sum of observations divided by n, so n it becomes an average. Look what happens to your average. And here, when you're here on the right, I don't think anything can move the average. That distribution tends to deliver mild tail events, so it can't really have, so no big shock will have a big impact anymore. Look, on the other hand, at fat-tailed variables. The average, you keep adding information, but your average keeps jumping. And of course, this is in norm L1. In other words, looking for the average, you could do it for any norm. And of course, things will get worse in higher norms. My research on this, I'm writing in parallel a book called Solid Risk, that has comprehensive work, and then there's something called incremental science. Incremental science, you take a simple point and you publish it. Not to lose, sight of the big picture. I made sure that they're synchronized and they're working together. So if I have to prove a point, I want it, put under scrutiny and put it in a journal, I put it here on the left. So I'm going to cover a paper with Cirillo, Pasquale Cirillo, on underestimation of violence using common methods, linked, of course, to the law of large numbers. A paper with Raphaël Douadi in Physica A we published. Something on Gini I'm writing, a very short letter, and of course a big paper on central limit and the problems. Central limit is the next step after the law of large numbers. And then, of course, the drafts of other papers connected to small little points, because I've been working on statistical inference under fat tails. Now, let's look at this tableau of fat tails. What you have here in this yellow color is what really works. And in other words, the place where the law of large number works. The general distribution means there's no randomness. And of course, you're going to get information from a single observation. Bernoulli is, you have 0, 1, minus 1, 1, these kind of variation where you just have two states. Thin-tailed from convergence to Gaussian, and there's something called sub-exponential. The cut point here is, for those of you who do finance, very familiar with the log normal distribution, it's an exact cut point right here. So beyond that, we leave the yellow area where the law of large number, the weak law of large number, doesn't matter, weak, strong, works beautifully, to what we call convergence issues. You're entering something that has a second moment here. This is category, is a power law, which we'll define. And then you have something that doesn't have a second moment. We call it the Lévi-Stavel basin. And then here there's this big important notion, forget about it, that with alpha less than 1, meaning the distribution doesn't have any mean, so you're going to be fooled, because in sample you will always see a mean. So let me define that class, the Pareto tail. Again, that class that is in white, we call it Pareto tail. It's formally defined as a variable that has that kind of x minus alpha asymptotic behavior. And of course, there's what we call here a slowly moving function. So you can have something in the body, and then when you go to the tail, it becomes a tail. So I'm not going to define fat tails here. I'm talking about statistical inference under fat tails. The simplest form of power laws, what we call power law here, this is really asymptotically what define a power law, are on the left. The easiest one to work with is Pareto 1. I don't know if it has 1 or 2 parameters, because it has a minimum value and alpha exponent. So the minimum value, I don't know if you need to calibrate it, if you call it calibration, if it counts or not. It costs you nothing, really. You just take the lowest value, and then, or you can set your value and only sample what happens above. 3 parameters in red is because that's what I use the most, where you have a scale, you have a location, the mean, for a Gaussian, but this is no longer, I mean, we're still in a location scale something called family of distribution, where you stay in a distribution if you divide x by s, or if you take minus m from x. So you move the distribution left to right, but for some, but we definitely stay in a scale family of distribution, but we have something that is different from the Gaussian. That the s here is no longer the standard deviation. In the Gaussian, if I divide x by s, you know, and of course s is normalized, and divided by s will be the standard deviation. So we'll map the standard deviation, which is the square root of the expectation of x squared, or x minus m squared. So now 4 parameters, the beta prime, you know, you can work with it. I like to work with it, but it's not that important because the additional parameter, because you have 4 parameters, the additional parameter may not be worth the cost. Again, when you go into the tail, it doesn't matter at all. The two-tailed, the student t, is a nice way for people in finance to model prices, but you can use a double Pareto. It doesn't make a difference because, again, the lower the alpha exponent, and of course the more fat-tailed, the lower the alpha exponent. The lower the alpha exponent, the more the tail matter, and the body basically provides no information. So you can have anything in the body, double Pareto, it doesn't matter. It's the tail that matters. And then here the Levy's table will work with it. Levy's table is quite important because you converge to it under summation, and we can do some analytics on Levy's table, and you don't need you know, to worry about pre-asymptotics when you work with it, because again, I mean, the Levy's table has, of course, the same tail alpha, so this is not going to be a big deal. Now, sample equivalence. I was writing silent risk, and I asked myself a question. We can go back to the first graph that we saw. I asked myself the question, on the left, of course, is a Gaussian, on the right is some power law. Did anybody make an equivalence of how much more data do you need for power law? It turned out that this has not been done. Why it hasn't been done? It hasn't been done, I don't know why. Maybe because statisticians aren't interested in power laws. Power laws usually are the domain of physicists, and physicists don't really care about statistical inference. They're really spoiled by nature being very clean and very neat. And so they, you know, and we have a lot of samples in nature. So the problem of sample equivalence never really came up, and it's not very hard to compute. So here I'm looking for the n indexed by p, the power law versus ng Gaussian. You set a number. I'm looking for a equivalence, okay, or table of equivalence, just for intuition and to realize how many mistakes people make. Something I refer often in my book, Pinker mistake. Why do I select Pinker? In my papers, I don't mention him too much, simply because it represents, this techniques represents the journalistic approach to saying, oh, this is my average, this is evidence. The sample is too stochastic for it to mean anything. If I take any of the distribution that we saw here and sum them up, we're going to go to that basin of attraction. If the alpha is below 2, definitely you'll go to a basin of attraction. The stable distributions, I can do some analytics, and I can do derivation, and I can find that tail equivalence between the two, which I did here, and it's quite a shock. The shock was as follows. When I was writing silent risk, I asked myself a question. I said, people, for some weird reason, select 30, n of 30 in a Gaussian as sufficient to bloviate about something. So I told myself, hey, you know, what if the data is Pareto? And the one that people discuss the most is a Pareto 80-20, meaning alpha of 1.16. How much more data? I said maybe 400, but then maybe I'm exaggerating, 400. So I asked around, people told me, oh, at least 200, or, you know, someone ventured to say 1,000. Yesterday, when I gave the talk, nobody came, you know, close to, you know, a high number that I was expecting. The number turns out to be 10 to the 14th, if you're adding an 80-20. In other words, you need so much more data if you just go by the mean to figure out what's going on. So, and also the speed of convergence, the alpha, of course, k over alpha minus 1. You know that when alpha is 2, which is asymptotic Gaussian, of course, it becomes square root of n. You need, as you're increasing, you stabilize at square root of n. So this is speed of convergence. Now, what remark I'm going to make here? The sample mean, or realized alpha average, or realized average in the language of finance, realized volatility, realized mean, realized whatever, is never Gaussian when alpha is less than 2, right? So it will be very stochastic. So in other words, if I'm going to compare, I'm comparing Gaussian to non-Gaussian, the non-Gaussian, I'm using a metric, so you know you got to work in absolute deviation, not in squared deviation, because the squares blow up. And even when alpha is higher than 2, you're still in trouble because the pre-asymptotics are very bad. That's, of course, my discussion of central limit. The good news is that the tail alpha can be estimated with maximum likelihood, as you know, standard maximum likelihood estimators, and it's very Gaussian. So here we have the average is not Gaussian, okay, just like the variable is not Gaussian, but the estimator of alpha is Gaussian. Plus, in addition to that, we can reduce the variance a lot more sometimes, but just doing a visual and doing what we call Zipf plot or visual plot, or some people call Pareto-Tien plots. And of course, we have extreme value theory, or we can do something called generalized Pareto distribution, where you look at exceedances. You set the so. An interesting thing, as we said, that alpha, if you use maximum likelihood, there's something called the Hill estimator that has, of course, problems, but still minute compared to the other one. Is effectively log normal, but as we all know about log normal distribution, you know, from work in finance, of course, log normal mimics a normal when sigma is small, and it becomes a normal rather quickly under averaging. You add observation, you're lowering the variance. And so look here, it's a log normal, the blue, it fits like a glove, and becomes normal under addition. And of course, the difference between the two fades very quickly, and it's not that relevant to do analytics, to try to pull out the distribution of the mean, the theoretical mean from here. So let's take a case study. Case study, I have a Pareto distribution. This is a distribution here. Of course, you know, only 2 parameters, not even 2, as we said. L is the cutoff point that you can arbitrarily set. Your mean is going to be, the expectation will be alpha over alpha minus 1 times, of course, L that acts both as a scale and strangely the mean. So that distribution is going to converge very quickly. And let's compare now sample mean to using this. This is what I get for small samples by taking the ratio of mean deviation. A reminder, you cannot use standard deviation like as in usual statistical theory, or you cannot use mean squares. You have to work with absolutes, because to stay in a norm L1. N of 1,000, look at the difference, and look at here. This one has very, 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 very high kurtosis. You still have, I had observation at 500, okay. I mean, of course, it happens at once every million, but you have to look at how the average behaves, okay. It's very skewed. Look at the other one, very well behaved. It's a Gaussian. This one will never be Gaussian, of course, because it is it would be a power law, you see. Realized average is a power law in the summation. It's actually a Levy stable with some parameterization. If I take a larger sample, remember we said before that the convergence happens at square root of n. We saw it from the speed, like you're adding information, and when the alpha is low, of course it happens very slowly. If alpha is 1, no information would add it. No observation would add information. So look, when you start increasing the sample, this of course converges at root n, and the other one doesn't. So the difference between them is huge. So here I have 100,000 n, and look at the difference between them. And of course, if you go to 1 million, it's going to be a lot bigger. Simple conclusion. You cannot use the mean to estimate the mean. that is a no-no, and I'm saying I'm using statistical theory. Okay, you cannot. There's no. You cannot estimate the mean. Use the mean to estimate the mean in Fourier power law. Okay, that's a no-no. You can show analytically from here that this is a great estimator. Okay, whether you use alpha distributed as log normal or normal, it doesn't matter much. Next, we're going to have a something more interesting. Okay, with alpha less than 1, there are cases that effectively appear to be power laws, but they have a little hitch that allows us to see the mean. So to see the difference between observed mean and realized mean. Case study in violence that I did with Sherry-Low. Here you can see in this one the difference between observed mean, okay, and theoretical mean, the true mean, okay, or the estimated mean. You see this one will be lower than that one, okay? And of course, the lower the alpha, the more wedge between them. And this effectively allowed us to work with an alpha of 55, 0.55, very, very low alpha, from a mistake I made early in my career in power laws. I was under the belief that when something has an infinite variance, okay, or something has an infinite moment, that affected because it's unbounded. If you put a boundary, say for example, now we're dealing with violence, no event can kill more than 7.2 billion people. I know it's a very remote boundary, but you can still put it there. I thought that if the mean was infinite, that it would be 7.2 billion. And that was my intuition, and effectively, Benoit Mandelbrot thought the same. And I realized nobody made the calculation of, hey, you know, what if we had a distribution that acted like power law under transformation, but transformed back into compact support? Okay, what would be the mean? Would it be on a high here? So if I have LH, lower bound L, higher H, which is the compact support of the true distribution of violence, L can be arbitrarily set, 5,000, 10,000, whatever you define as violence, you know, as big violence under consideration. And H is the exact maximum number that violence can kill. So it's really technically unbounded, but not technically, but it has a mean, okay? And then we do a transformation of phi into something that has removed the compact support on one side. Phi has to satisfy some condition. I use this one. You know, people in finance do it all the time. We have stock prices can be between 0 and infinity by taking a log of prices, of relative prices. Then you open it up on the left side, so you do you're on a real line, minus infinity to infinity. We can perform analytics on power law, and then come back, reconvert back, and they, of course, got to be the same parameters. That's the beauty of it. Okay, and it's just like in finance, whether you work with normal or log normal, it's the same parameters, but they mean different things in different distribution. And look, we've got beautiful fit. I've never seen anything like that for the near tail, which is my department, and Sherry-Low, who deals with extreme, got a beautiful performance on a far tail. That's for violence. I'm not talking about violence. This is more of a methodology thing. And this allows us to compare the true mean to the sample mean. Because again, let's take these distributions. They have something very weird to them, is that they're dominated by rare events, and these rare events are rarely in the sample because the right tail is not seen. So, and I discuss it at length in the Black Swan. People don't typically get it until I draw the graph or show them the mass. Is that 96% of observations, for example, something like this, are going to fall below the mean. So odds are, when you observe a sample, it's going to underestimate its true mean until that observation comes to, you know, put it back in place. So it's just like in finance, you know, you observe until the crash, all right? You don't have an idea of how bad things can be on the left. So that's a nice exercise where working with the distribution of alpha, and you can stochasticize alpha and look at the range of alpha, you can get an idea of the mean, okay? The second point, let's apply this to Piketty thing. I mean, I love the idea of inequality is not good and stuff like that. That's not the point. The point is methodology, okay? That and it starts smelling. So people start talking about centile contribution, okay? centile contribution. I thought, hey, these guys are talking about a mean, and they're accepting that it's a power law, and they're expecting there's concentration, they're accepting fat tail, just like with the Pinker fellow. He accepts it's a power law somewhere in page whatever, and then the other page he starts talking about changing the mean. They're making, of course, a very small mistake compared to the, so just making a journalistic inference from the mean, but still there's a problem there. So I smelled it, and I just got on my computer and did the Monte Carlo, and of course did some analytics with Raphael Douady, and we discovered the following. If you observe 80-20, which by recursing gives you top 1% has 53%, if that's what you observe, effectively the top 1% would have more like 75%. But it's just that the way you measure from the average, the centile contribution, you say the top 1% had this share of the total, means you're taking the mean for that conditional mean, as we do here. You're taking that conditional mean divided by the total mean. Okay, that's how it's really done. So we're taking a ratio of two means, one conditional, one unconditional. That's the quantile contribution. And you're definitely going to have that bias simply because the mean is not a variable for these things. The location of the distribution may be variable, but not the mean. Anyway, so, and this is the bias. Okay, if I have a sample of 1,000, and the true ratios of the top 1% should have 65% and 66% of the total. The mean, all right, the LC, the variable would be 0.4. So it'll have a huge estimation of 0.25, you see. Why? That's the problem with the distribution. And when you go to 100 million in your sample, you still have a huge bias. And not a sample, in your population. It's why? That's the situation. But when you go via the alpha, you estimate the alpha, you don't have that bias. Again, this is strange. The same applies to what's called Gini coefficient. This is the coefficient, also a drink. With the Gini coefficient, again, you're talking about relative mean. Sorry, not relative mean. The difference, the mean difference, absolute difference between all your variables. And if the Gini is 1, it means you have maximum inequality. If the Gini is closer to 0, it means that everybody's making exactly the same amount of money. So, and then these are the two ways they measure the Gini. This is the theoretical. This is the thing here. For a power law, that's a Gini. The Gini comes, has distribution from the alpha, pull the distribution, and effectively, when the true Gini is 0.83, and you look at small population, you get 75, a huge bias. And then, as your population increases, as with Piketty, you're going to see more inequality. That's just the system. So, I will stop here. We can continue now in a second moment. Because, as I said, no null one. Thanks. Finally, let me say something. I am not saying that measuring the way we're measuring is going to give you a perfect answer. I am saying if you are going to do statistical inference, these are the variables to work with. Things can be more complicated under conditional alpha, under all these, that's fine. But if you're going to work with something, work with the alpha. Okay. If you work with the wrong variable, you're going to get the wrong answer. And this is very prevalent. Actually, in the end here, I'm going to skip this section here, that much of finance, social science relies on bogus estimators. And no wonder why, when we talk about volatility, we have to recalibrate models because they're not estimators. You're chasing past fitness. If you have to, we don't recalibrate the speed of light, but in social science, they keep recalibrating something. Why? Because they have the wrong variable. They quants every day recalibrate their models. It is offensive. See, so they're chasing past fitness. As the great Benoit Mandelbrot said, when lightning hits, we do not change the law of nature, right? It should be the same. You should, we recalibrate the speed of light. We had made a few mistakes maybe, and then we zoomed in on it, and that's it. Now we converge to it. So it should be maybe not the same, but your calibration error over time should decrease. But here, no, we still have the difference between calibrated model and delivered doesn't seem to shrink, which is why most of social sciences is largely bullshit, particularly when you're dealing with microvariables. Now, excellent news is that rigorous methods, extreme value theory, can help us get closer. But again, we're not getting very close. One more thing I want to add here is that when I look at these classes of distributions, one thing I want to add. When you look at these distributions, you have to remember that things fool you downwards, not upward. In other words, a power law can disguise as a Gaussian in small samples, but a Gaussian cannot disguise itself as a power law. I call that in the Black Swan the masquerade problem. In here I showed it, I talk about the tail dominance. Something that delivers a jump of 500 standard deviation cannot possibly Gaussian. Okay, so you cannot be fooled by a power law. You can be fooled by a Gaussian. So there is some kind of dominance in the way you select your distributions. Thank you for listening.